Here's a question from the 2008 BC exam. This was actually a calculator question, and what they wanted you to do is use this table of values for a function h and a bunch of the derivatives of h to do some work with series. So this is another question that involves series here. In part A, it says to write the first degree Taylor polynomial for h about 2 and then use it to approximate h of 1.9. Well, you're going to have to know what the definition of a Taylor polynomial is in order to carry that out. Now, this is the definition of a Taylor series. So we're going to take the k value of 0, 1, 2, 3, however far we have to go, put those numbers in place of these k's, meaning we're going to have the function evaluated at where our series is based, the first derivative evaluated at where our series is based, the second derivative evaluated where our series is based, and so on. This factorial is going to go up by 1 every term, as is this power on the quantity x minus c. So if you know this definition, which wasn't provided here, what you can do is you can construct your first degree Taylor polynomial, meaning you want to have something that has an x to the first in it and no powers of x above that. And it has to be based at 2. So you see right away I have x minus 2 to the 0, I have x minus 2 to the first, there's my 0 factorial, there's my 1 factorial. Then I needed the function evaluated at where the series is based, in this case 2, and I needed the first derivative evaluated at where the series is based, and again 2. These values are sitting up in this table, right? H of 2 is 80, right? H of 2 is 80, and then h prime of 2 is 128. So if I scroll down a little bit here, I've just taken this line, simplified it a little bit, and I've written out my first degree Taylor polynomial for h about 2. And then it asks us to approximate h of 1.9 by using it. So h of 1.9 can be approximated by tossing 1.9 into our first degree polynomial. So if you put 1.9 in place of this x and then toss this into the calculator and evaluate, you end up with 67.2. It does ask you to explain whether or not it asks you whether this approximation is greater or less than h of 1.9 and to explain your reasoning. Now I've said right here that h of 1.9 is going to be above the first degree Taylor polynomial approximation at 1.9. And the reason why is because there's this little bit in the problem statement about the function h and its 4 derivatives all increasing on the interval from 1 to 3. What that would mean is that our second derivative is increasing. And the reason why I'm looking at this column for the second derivative is we have a positive value, and then it gets to be a more and more positive value as the x value gets carried forward. Why is the second derivative going to help us answer this question? Well, a first degree Taylor polynomial is always going to be the line tangent to the graph at where the series is based. This series is based at 2. So this first degree Taylor polynomial is really the tangent to the curve at the x value of 2. And since the function has a positive second derivative on this entire interval, our function's concave up. And what that means is if you have a function that's increasing and concave up and you have a tangent line to the graph, the tangent line and the graph are going to intersect at the point of tangency, but the graph is going to be above the tangent line everywhere else on that interval. So the value on the function is going to be bigger than the value on the line at 1.9, and that has to do with the concavity of h, which we can deduct from the table there. In part B, they want us to kind of take this a couple steps further. Now they want a third degree Taylor polynomial for h still based at 2, and we want to use it to approximate h of 1.9. So we're going to use the definition again. We have the same 2 pieces that we had on our first degree polynomial. All we have to do to go to the second degree polynomial is we have to tack on 2 more terms to get an x to the thirds to pop up somewhere. So our first term that we left off previously is going to be the second derivative evaluated at 2 over 2 factorial. There's x minus 2 to the second. And then we also have the third derivative evaluated at 2 over 3 factorial times x minus 1 to the third. So this would be the generic version of our third degree Taylor polynomial. You want it to be specific for the function h. Well, you've got the second derivative in this column evaluated at 2. So I put that in place of h prime of 2. You've got the third derivative evaluated at 2 sitting right here, so I put that in place of h triple prime of 2. Just kind of simplified a little bit, simplified this fraction when I go from this line to this line. And then we want to use that to evaluate to approximate h of 1.9 again. So we're going to evaluate our third degree polynomial at 1.9, put 1.9 there, put 1.9 there, put 1.9 there, toss that into the calculator, and you get a value that's relatively close to what we got with our estimate in part A. We get 67.988. This will be a little closer to the true value of h of 1.9 because we've used more terms in our series. So the more terms we tack on within these estimates, the closer our estimates are going to be. It doesn't really ask us to say that, but you have more terms present within this estimate. Therefore, we have a better estimate for h of 1.9 as a result. Last piece of this is the trickiest piece. They want us to use the Lagrange error bound to show that our third degree Taylor polynomial for h at 2 approximates h of 1.9 with an error less than 3 times 10 to the negative 4th. So this is our estimate from part B. We want to prove that our estimate is going to be within this amount by utilizing a Lagrange error bound. Well, I'm going to first start by defining the remainder. If I use the first 4 terms, which would be our third degree polynomial for h about 2, my remainder is going to be expressed by this. So this is a definition that you would have spoken about within your Taylor-Maclaurin series section, and we would take the absolute value of the first term of our polynomial that we've left off, and that would be the 4th degree term. So we see an x minus 2 to the 4th here. We see a 4 factorial here. We see a 4th derivative here. The weird thing is that we don't have 2. We don't have the value where the series is based right here. We have this new variable being defined, z. Now what's special about z is that z has to sit somewhere at or between the value of x that you're making your estimate at, and in our case that was 1.9, and the value of x where your series is based, and in this case that's 2. So z has to come from between 1.9 and 2. So what the definition of the remainder is that there's some z in between these numbers that would have this quantity make up the difference between our estimate and the actual value we were trying to find perfectly. It's very difficult, if not impossible, to pin that value of z down. So what we call the Lagrange error bound is we call the Lagrange error bound the maximum value of this remainder. So basically what you're trying to do is you're trying to figure out when this numerator is as big as it's ever going to be based on where z has to sit. Well, in this case, the 4th derivative evaluated at z, when z sits between these numbers, is going to be biggest at 2. The reason why goes back to this. These 4 derivatives are increasing. So as z goes from 1.9 to 2, the value of the 4th derivative evaluated at z is going to continue to increase as we progress through this interval. Therefore, the maximum value of this remainder is going to happen when z is equal to 2. And h, the 4th derivative of h evaluated at 2, is something you can take from the table. Right? The 4th derivative of h is here. Evaluated at 2 is this number here. If you toss that here, divide by 24, and then also evaluate the negative 1 to the 4th, and I lost my absolute values here for some reason. What you end up with is you end up with positive, if you take the absolute value of this quantity, positive 2.704 times 10 to the negative 4th. Well, in scientific notation, this value is going to be less than 3 times 10 to the negative 4th. Therefore, we've established that our Lagrange error bound proves that our estimate from part B is accurate to within this amount.